Have you ever stopped to think about how massive companies, with thousands of employees, keep their computer networks from just collapsing into total chaos? Well, today we're pulling back the curtain on the invisible system that makes it all work, Active Directory replication. This is the secret sauce, the engine that makes sure every single change, from a simple password update to adding a brand new user, gets synced up across the entire system. All right, let's get into it.
So picture this. You change your password on your work computer, you grab your laptop, you run to a meeting room, and you try to log in. Boom, access denied. Your new password doesn't work. How frustrating is that, right? Well, that exact scenario is the kind of chaos that Active Directory replication is built to prevent. It's the silent hero working in the background, making sure that when you make a change in one corner of the network, that change is recognized everywhere else, almost instantly. So how does all this magic actually happen? We're going to follow the journey of a single update, kind of like a digital detective story. We'll start with the big challenge itself. Then we'll uncover the two very different roads an update can travel down. We'll follow the express route, check out the mail-in option, and see what happens when it finally reaches its destination server. And at the end, we'll talk about why this whole thing matters so much. Okay, so here's the fundamental problem we're trying to solve. A big network has a bunch of different servers, what we call domain controllers, and each one holds a copy of the company's entire directory. Now, if those copies aren't perfectly identical, you get chaos. The whole goal here is to create a single, unified source of truth so that every server has the exact same information at the exact same time. Right at the heart of this whole operation is a super important component called Ntdsa.dll. Now, a DLL file is basically just a shared library of code that lots of different programs can use. This one, though, is special. Think of it as the air traffic controller for every single update. It sits deep inside the operating system, orchestrating every change and making sure nothing collides. It's the real brains of the operation. So how do updates even get to our air traffic controller in the first place? Well, they usually arrive using LDAP, which stands for Lightweight Directory Access Protocol. You can just think of it as the official language that applications use to talk to Active Directory. When you change your password, your computer sends an LDAP request, and that is the starting pistol that kicks off this whole replication journey. Okay, so our air traffic controller, Ntdsa.dll, has just received that update. Now it has to make a big decision. It needs to get this new information out to all the other servers on the network. And funny enough, it's got two completely different ways it can send the package. And here are our two delivery options. On the one hand, you've got RPC, or Remote Procedure Call. The best way to think about this is like an express courier service. It's super fast, it's direct, and it's the default go-to method for most updates. Then, on the other hand, you have SMTP, the same protocol that powers all our email. This is more like the standard postal service. It's reliable, for sure, but it's not designed for speed. It's used for very specific situations, like sending updates between different office locations. All right, let's follow our password update down the fast lane. We're going to trace its journey along the RPC Express route. This is the path that's used almost all the time for updates happening within a single physical location, like one office building. What's really cool here is how all these little pieces work together as a team. First up, you've got a component called LDAP32.dll, which helps your computer make the request. Then Ntdsa.dll steps in and acts like a negotiator, handling all the back and forth with the server. And finally, a little packer named ASN.1 encodes the whole request into a neat, safe package that's ready to be shipped across the network. So, the whole RPC journey is super efficient. Step 1, the request is made. Step 2, it's packaged up nice and tight. Step 3, it's sent flying across the network. And step 4, on the other side, the receiving server's own Ntdsapi.dll is there to catch it. It's clean, it's direct, and it is incredibly fast. But what if the servers aren't in the same building? What if they're in different cities or even different countries? Well, that's when the system might switch over to the mail-in option, SMTP. This method is specifically designed for sending updates between different physical locations, especially where the network connection might not be as fast or reliable. Now, for this postal route, we've got a whole different crew. The main player here is a program called ismserve.exe. You can think of it as the mailroom clerk. Its job is to take the update, use a special tool called the CDO library to stuff it into a digital envelope, and then hand it off to the SMTP service, which is basically the mail carrier that actually delivers it.
The SMTP journey is definitely a bit more patient. First, the update is packaged into a file, kind of like a letter. Then it's placed in a digital mail queue, just like letters sitting in a post office box waiting for pickup. The mail service then comes along, grabs it, and sends it on its way. At the destination, the receiving server's own mailroom clerk, ismserve.exe, opens it up and applies the update. It's a classic store and forward system built for reliability when speed isn't the #1 priority. So our update has finally arrived at its destination, whether it came by that high-speed courier or through the standard mail. But what happens now is probably the most critical part of the entire process, actually writing that change into the local database without breaking anything. This is where a very specialized component called the replication subsystem takes the stage. Its one and only job is to perform what is essentially delicate surgery, writing the new information into the database, making absolutely sure the change is applied correctly and doesn't corrupt any of the existing data. And here we are at the final handoff. The update first goes through a protective layer called an API. Think of it as a security checkpoint. Then, a really powerful database engine called ESE takes the data and permanently writes it into the core database file, which is called Ntdsa.dll. And just like that, our password update is officially complete. The change is live on this server. Wow. Okay, we've just covered a lot of pretty technical ground. But the big question is, why? Why go through all this complexity? Well, let's step back for a second and look at the huge benefits of having a system designed this way. At the end of the day, the payoffs are enormous. First, reliability. Having 2 different delivery methods means an update almost never gets lost in transit. Second, scalability. This architecture is what allows a giant global company to have one single synchronized network across every continent. Third, integrity. That whole layered approach we saw protects the core database from getting corrupted. And finally, efficiency. The high-speed RPC method means that for you, sitting in your office, changes feel totally instantaneous. It's a system truly built for resilience and scale. For decades, this has really been the gold standard for keeping networks in sync. But, as the world keeps moving more and more to the cloud, to decentralized systems, you have to wonder, what's next? What will data replication look like in the future? It's a pretty fascinating question to think about. Thanks so much for joining me for this explainer.